Did you see that? Maybe just play it in slow motion. That was an object that I threw across my classroom. Why did I throw it across my classroom? Because I wanted to show you the path, the trajectory, the path that particle actually took. Okay? It was in the shape of a parabola, which is just one of the many, yes, I said many, one of the many reasons to love the parabola. It is a fantastic graph because of gravity for a start. When you throw an object, it will, wind resistance aside and other resistances also aside, it will form the path of a parabola. Every time you watch a cricket match, a football match, see a rugby ball being kicked, you are seeing a parabola in motion. That's just one reason why this is fantastic. Another one is this, okay? You probably never thought about it before, but your satellite dish that you use to watch your TV is in the form of a parabola. The French call it a parabola, hence parabola, and this is the focus point, which I'm going to be talking about in the next presentation, okay? But this here is in the shape of a parabola. Doesn't that look absolutely lovely? And there are other things as well. For example, not just the gravity thing, but quadratic equations. Who does not love a quadratic equation? If you don't love a quadratic equation, I'm sorry, but you're watching the wrong video. Why did you tune into this video if you don't like quadratic equations? Because the parabola is all about quadratics, isn't it? Okay, it's so good, even the Italians named a corner of the Monza Grand Prix after the parabola. They call it the Parabolica. If that's not enough reasons to love the parabola, I don't know what is, okay? Let me just give you some more then. Architecture, okay? Architecture. When you look at a suspension bridge, whether it's the Clifton Suspension Bridge, Bristol by the way, or whether it's another one, okay? Maybe the Golden Gate Bridge is probably the most famous example, okay? You are seeing a parabola when you look at the way that the, whatever those things are called. I know it's called a parabola, what are those things actually called? Cables, let's call them cables. You're seeing how the cables are actually formed, okay? So there's lots of reasons to like the parabola, and I'm going to talk to you about the mathematics of the curve and the parabola coming right up. Stay tuned. Here we go. Everything we need to know about the parabola is on this page. In that respect, it's a little bit easier to come to terms with than the ellipse or the hyperbola. If this is the third one you're watching, you're going to find this one a lot easier to get to grips with. If this is your first one, well done, because you've chosen the easiest one to look at. The hyperbola and the ellipse on separate videos, they're a little bit more complex, okay? Well, one thing that makes it easier is that there's only one focus point and there's only one directrix. For each focus point is one directrix, okay? And the focus point is given there, SA0. A lot easier already to remember than the ellipse and the hyperbola. And correspondingly, the directrix is x equals -a. Now, why do we need a focus and a directrix? Why is that important in terms of the parabola? Well, it's because of what defines a parabola. The parabolic path. How do we know it does do this? How do we know the curve is exactly like this? It's because of what's called the focus directrix property. The focus directrix property. That's a really important point. Now, this is what it is. You take any point on the parabola. Now, I've chosen a point P there. Don't worry about the coordinates, how I've labelled it. I'll talk about that in a minute. Any point P there, the distance between that point and the focus point is always the same as the distance between the point and the directrix. Even if it doesn't look like it on my graph, it always is. Okay? It always is. And that's a really rather fascinating fact about the parabola. The way that it's defined, it's the locus, we use the word locus, the locus of the set of points such that any point P is always the same distance, sometimes we use the word equidistant, from the focus point as it is the directrix. What a fantastic fact. And for that reason, there's only one path then it can actually follow for a particular focus point. Alright? So that's why the focus directrix property is really important in terms of a parabola. In terms of the general equation, when it's in this form, y squared equals 4ax, called the Cartesian equation, and the a there is the a there in the focus point. So the great thing about that is, if you're told the equation, for example, y squared equals 8x, obviously you can work out a is 2. And then you've got the focus point already, 2, 0, and the directrix, x equals -2. There, there's a couple of exam questions answered already. Well, part of exam questions, shall we say. In terms of how we define it parametrically, it's given by these: x equals at squared, y equals 2at. And that is why I've labelled this point here, p, as ap squared 2ap. Because it's quite common for a general point to be given x and y coordinates in terms of the parametric equations. Okay, so you notice that for a point P, I'm calling it AP squared 2AP. For any other points, like there, Q, because it could be any point in the parabola, usually we use P and Q for two separate points, you'd call it AQ squared 2AQ. Okay, so the parametric equations I find very helpful because it tells us straight away what x coordinates and what the y coordinates are. But how do you confirm that these parametric equations work? Well, we just convert them into Cartesian equations. I'll just show you how. So here we go. If we just begin by making t the subject in the parametric equation for y, we would have t is equal to, what's that going to be, y over 2a. Okay? Then we'll just substitute it into the parametric equation for x, and so x is equal to at squared, which is going to be a times that squared. Yeah? So a y squared over 4a squared. And that simplifies to x equals y squared over 4a. Hence, bring 4a over there, y squared equals 4ax. Okay, so that's quite simple. And that's pretty much all you need to really know about the parabola. I'm hoping you found that useful and interesting. Well, there it is. I hope you liked my presentation on the parabola. What's going on behind me? Just another cool aspect of the parabola. This is an actual rocket launch as viewed from an airplane. Isn't that amazing? Okay, even though a rocket has been launching with all that power and all that speed to try and break the pull of the Earth's gravitational pull, it's still forming the flight path of a parabola, isn't it? Because gravity is still trying to pull it down to Earth. As hard as it tries to break the pull, gravity is still trying to pull it downwards, okay? Isn't that absolutely amazing?